Let's do a quick introduction to the next unit we're working on, which is functions in mathematics. And the idea of a function is, at least one way to think of it is as a machine. You provide the machine a single input. The machine carries out some kind of a rule-based operation and then produces one output. For each input, it produces one and only one output. Now, the rule inside the machine could be a mathematical rule, or it could be an other kind of a rule. For example, when you input something on a field on a screen on a website, you're inputting something, let's say your name, the machine is doing something, some kind of a rule. It's maybe looking up your name in a database, it's checking to see whether your password matches your name, and then it's producing an output. The output might be either it allows you to go forward, or it says your password did not match, in which case you'd have to re-enter. So without numbers, we can think of a function as, let's say, something like this, the initial function. The input might be your name, Alfonso Green. The output is AG. The rule is you combine the first letter of each of the different words in the name, and that creates an initial. So Jean-Claude Killy produces JCK. Lina produces LN. Dom Inate produces DI. So those would all be a function. One input was the name, and one output, which was the initials. And then the rule that assigned the output to the input was in this case, taking the first letter of each name in the person's larger name. So, and then here's another way of thinking about a function. A function tells each input where to go, in a sense. So, for example, let's say that you are, in this case, we have the room corner by season function. The input is the student's birthday. The output is one of the four corners of the room. Let's say the rule would be that if your birthday's in winter, go to the front left. If it's in the fall, go to the front right. Spring, rear left, and summer, rear right. And so each student would know where to go, and each student would have only one place to go, but each student would have a place to go. That makes it a function. Okay, let's do another one. Room corner by color of clothing function. Input, color of student's outfit. Output, one of the four corners of the room. Red front left, blue front right, green rear left, yellow rear right. Here's the problem. It's unclear for a student where they should go because they might be directed to the front left or the front right because they might have a combination of colors, or they might not be wearing any of those colors. This is not a function because not every student would be assigned a place at all, and some students might not be sure where to go because they might they might have a reason for going to one or two or three different corners. That would not be a function. So a function rule then is the rule that assigns each element in the set of inputs to an element in the set of outputs. So for example, here we can represent a function with this mapping. Each arrow represents the function being carried out. In this case, this particular input is assigned to two different outputs. This input is not assigned to any outputs at all. This is not a function. This mapping is a function. Each input is assigned to one and only one output. Now, it's okay for two different inputs to be assigned to the same output, but it's not okay for one input to be assigned to two different outputs. Then it's no longer a function. That, very briefly, is what a mathematical function is. So as you recall, we had this GeoGebra app where we had a rectangle, and we could control the width of that rectangle basically by moving that blue point along the x-axis, and that value x is equal to the width of the rectangle. So when I set x equal to, let's say, 10, then I know that the width of the rectangle is also equal to 10. The other thing you'll notice is that as I change the width, the height of the rectangle changes. So when the width is 10, the height is 6. When the width is, let's say, 8, then the height is also 8. When the width is 6, then the height is 10. And so one of the ways that we can think about that is that if we look at a table of values, you can see that whatever x is, that the height of the rectangle is just going to be equal to 16 minus x. So when the width is 0, which means we don't really have a rectangle, the height is 16. When the width is 3, the height is 13. When the width is 11, the height is 5. So for each value of x, there's a height that goes with it. So as x changes, the height changes. And so therefore we can define what we call a function of x, which we will call height of x, or height given x. And what that means is that for any value of x that I can plug in, this function will tell me what the height is for that given width. So for example, when I plug 11 into my function, height of x, then I would get an output of 5. Because the height when x is 11, the height is equal to 5. The rule for that function is 16 minus x. What makes it a function is that for each value of x that I can plug in, there is one and only one output. So there aren't any values of x for which there is no height, and there aren't any values of x for which there are 2 different heights or 3 different heights. There's only one height. Notice that our values of x go only from 0 to 16. That's called the domain of our function here. It's the set of all the numbers that we can plug into our function. And you'll notice that the reason is that it wouldn't make sense for x to be negative, and it wouldn't make sense for x to be greater than 16, because then our rectangle actually would have a negative height, which wouldn't make sense. And so we can then think of this as a table of values, where we have our values of x, or at least only the integer values, and the heights that go with that. We could also think of that as represented by a graph, where along the x-axis we have the value of x, along the y-axis we have the height. And you'll see that as we change the width at this point representing our current situation moves, and so that as x gets smaller, the height's actually getting bigger. Now another way that we could represent that is with what is called a mapping, where we just have, for each value of x, we have an arrow that points to the corresponding value of height of x. And so as I move my value of x along, I can see, well, my arrow keeps moving as well. So the input side keeps moving to correspond to the current value of x, and the output also moves the end of the arrow to correspond with the height of the rectangle that goes with that given width. So when our x value, or the width, is equal to 10, the height is equal to 6. Now, right now we're only looking at the height, but we could also look at another measure of this, which is the area of this rectangle. And you'll notice in here that we can see that when x is 10, then area of x, or area given x, is equal to 60. What that means is that when x is equal to 10, the area of the rectangle is equal to 60. And again, you'll notice that area, the function area of x, keeps changing as we change the values of x. And so you'll notice here that we have another function defined, area given x, and the input is again the same value of x we used in the previous function, which is just the width, but now the output is the area. And the area is just going to be equal to the height times the width. And we already know that the height is 16 minus x, the width is x, so it would be x times 16 minus x. You'll notice that when we graph it now, we have a very different looking shape. First of all, it's not straight, it's curved all the way. It also starts at 0, ends at 0, and hits a high point in the middle. And you can see that what that corresponds to is that when our value of x is equal to 8, we are at our maximum possible area. And that area is equal to 64, 8 times 8. A little bit below 8, our area is lower, 62.75. And a little bit above 8, our area is also lower, Here again, actually, it's 62.75. So on either side of this maximum area, we have areas that are the same for two different values of x. Now, is this a function? Well, let's look at the table. We still have, for each value of x, we have exactly one area. There's no value of x that gives us two areas, and there's no value of x that has no area associated with it. Now, there are some areas that are repeated, but that's okay. That's still a function. As long as each value of x has one and only one area associated with it. And that's what we can see here. And again, when we look at the mapping version of this, we can see that for each of these that there is a value that is associated with our given value of x. And so we can see that as we move x, our arrow keeps pointing to different values, but as soon as it gets below 8, it starts repeating values. So when both are at 0, we start at 0, the area goes up to a high of 64 when x is 8, but then it starts to come down again. And that's also represented graphically here. So we can see there's a lot of different ways of showing this function. We can show it with a graph, we can show it with this mapping diagram, we can show it with a table of values, and then we can just show it dynamically here as we move this value of x. We can see that the area associated with that value of x changes. Now we also can change it so that what we're looking at is now the diagonal, and everything works the same way. For our given value of x, we have a given diagonal, and you can see the graph now looks different because the diagonal is the longest when the rectangle is either very narrow with a great height or very wide with a very minimal height. And right in between, the diagonal is at its shortest. And you can see that on the graph. You can see that in the table. And then you can also see that in our mapping when we change the values of x. You can see that we reach our lowest diagonal value right when x is equal to about 8, or exactly equal to 8. And again, for each value of x, there is one and only one diagonal length, and that means that, again, we have a function. Now notice for the last of these, the perimeter, a couple things. First of all, notice that our graph gives us a straight line. Notice what happens as I move the value of x. You can see that in the box here, perimeter x, which is the perimeter of the rectangle given the value of x. So when x is equal to 2, the perimeter is 32. When x is equal to 6.72, the perimeter is still 32. And when x is equal to 11.68, the perimeter is still 32. That means that when we graph it, we just get a straight line where, because it always has a value of 32. When we look at our table, every single value is 32. When we look at our mapping here, no matter what the value of x, it always points to the same value, which again is 32. Now, this is an unusual function, but it is still a function because every value of x has one and only one perimeter value associated with it. And so that means that we do indeed have a function.